My name is Hector. I am an adjunct professor at the Department of Mathematics in Montgomery County Community College. It's a suburb of Pennsylvania, but I don't live really in Montgomery County. I live in another suburb of Pennsylvania, of Philadelphia. And yeah, it's great. Teaching differential equations is great, and math is great. We have a great mathematics department, very like open-minded. So we are also creating our own culture of simulating or modeling scenarios. And this has been great, a great find by Professor Von, who is in the audience, to have found Simio and a collective of like-minded professors that want to use simulation and modeling for the differential equations class. So it's really great. So do I start?
Yes, please.
I already started, yeah. So the title of the talk is Illustrating the Dynamics of Gliders using Differential Equations and Flight Simulator. So this is a one-day experience that we do in my differential equations class. So it happens in one class. So I will tell you a little bit about my projects in differential equations and the projects that I do with my students, and the kind of learning experience that we provide to our students when we engage into this type of project or activity. Then I will tell you very briefly about the dynamics of gliding motion. We solve the equations in the Wolfram cloud. I ask for permission. Some sales representative, helped us say that yes, we can use it for free, at our college at least. And then what we do is to gamify. So we use a flight simulator to actually compare the predictions of the differential equations with the flight simulator. And then there is a student research project that is available for the students to partake on gliding motion. So let's see if next. So I know a lot of differential equations, but most of them, they are too difficult. So they are not familiar to the students, or things like they need to know electromagnetism or quantum mechanics that is some things that they might not know. So I found a Reddit about fun differential equations. And this user, Taximes, has dynamical models of happiness by Sprott, highly recommendable paper, and Zukowski's model for simple gliders. So pulling that thread, these are the projects that I work on simultaneously with my students. So they separate in groups and they choose one of them is going to be their project for the second half of the semester. And there will be either one day every 2 weeks, office hours. We use it to work on these projects. Once they finish the project, they do a presentation at the math club with the results as a group. And there is the dynamical models of love, the most popular project. Dynamics of simple gliders, 4 people joined there. So the engineering type of students, they joined there. Delay equations and models of neurons, etc. So this is the paper. Well, if you click on those links, you get a primary source, or secondary in this case, which is this chapter about gliding motion. And it has the forces and the equations. So yes. So what we do in class is to derive the equations. There is a part of the class that is deriving the equations. And the other one is programming this into a computer. And then we also illustrate the solutions by computer game and encourage the students to do the same. And then they have a project available on gliding motion. They can do whatever they want with the computer code. So they can explore and try to come up with something. I will show you an example at the end. But the idea of doing this is because at the Montgomery County Community College, we have Professor Bone, and he has been kind of like a leader on gamification, certainly at our college, but I would say even beyond that. And he has a NASA grant, a 1-credit course that he teaches. And the general idea is to use the computer game as a kind of experiment to illustrate topics from algebra, topics from differential equations, stuff like that. So this is a bit doing the same thing, So dynamics of gliding motion, force is equal to mass times acceleration, and then the forces are going to be the gravity force that pulls the plane down, the drag force that slows it, so it's opposite to the velocity, and then the lift force that tends to lift it. So if you can see here, it's kind of nice. And there are these vectors, which are time dependent, this unit vector. So that's interesting because that's a vector calculus topic. And these are the vectors. This v hat is a vector in the direction of the velocity. So the drag force will be opposite to that. There is also, a vertical downwards vector, and then this theta vector that is going to be perpendicular to v hat. And the forces are going to be gravity force here in white, and the lift force in green, and the drag force in red. So then solving the equations, you substitute the forces for the expressions. Then this J, you can write it in terms of theta and v. And then you have to take into account that the derivative of the velocity, the time, this unit vector depends on time. So you have to take the derivative of that. But once you have that, you get the equations and you separate the components and you get these two simple, rather simple looking, innocent looking equations, which are the ones that we solve by computer. Are the same, they are called Zukowski's equation and they are in the paper. The difference is I like to have this drag parameter and lift parameter rather than having drag coefficient and lift coefficient, because it makes it simpler, less numbers to put in essentially. But the students also get these formulas for the drag parameter and the same for the lift parameter. So that they can put things like the atmospheric density or the particular aerodynamic area of the craft, as well as numbers there. And then, well, we derive it in class. This is the class. So you can see that I go first very kind of orderly. And then I start losing control, and everything becomes of the same color. I go then on the top, and then I come back through here. And finally, I arrive to the equations. And this is a part of the class that is doing this. So the equations we solve them in the Wolfram language. And it's amazing, the Wolfram language, because it's just, it's not my ideal language because it's not free. But it's an amazing language in the sense that it's so easy to code, So the code that I give the students looks like this. Let me give you the code so you can have it. So I'm going to put it in the chat. So I have to go into one of my 20 windows here. And maybe it's this one. Yes, here it is. So that's how I interact with the students. I gave them the code, and this is also, and then you get something like this. If you click in there, and if you have an account, probably if you have an account, you will be able to open it. Otherwise, you may not, but you make your own copy. And then you have your own copy that you can edit. And then the students use it, and this is by word. So I asked the sales representative that they allow us to do it. But it was 2 years ago. I should ask again, I guess. Yeah. So then you have a simple code like this. In this case, it's plotting the position, the vertical position as a function of time, the trajectory, which is a parametric plot of the horizontal position, vertical position. And then it's comparing, because I also have here these numbers. These numbers are coming from the experiment. Let me show you the experiment. So I'm going to go here and reload this. And then we will see, I will have to switch off the engine. So you see these gauges. Those are data that you can use. Let me switch off the engine if I can. I don't know if I can. Come on, engine, switch off. Oh, there it is. Oh. It's not switching off much. Let's see what happens. So you can see that it's kind of going down. Let's put it in such a way that maybe we can see it like this. So it's going down. Let's see if it recovers a little bit. So you can see now, if you look at this gauge with the artificial horizon, the second gauge from the left, you can see that it's leveling. You can see that it's leveling up. It started going down like this, and now it's kind of leveling up somehow. And then it might go down again. So let's see if I can, yeah, like this. So now it's kind of horizontal, and then it's going to actually nose down, going nose down again. The engine is off or almost off. And you have data like the altitude that you can take. So if you have like a stopwatch and a notebook, you can gather data. And well, now it's about to crash. So let's go back to the presentation. So that's a simple code like this. You know, you can actually explore those things. So let me show you the data itself. So this is the data. So if you remember at the beginning, it was going nose down, and then it kind of slow up a little bit, and then it went like horizontal, and then it went down again. So this data that I'm showing here, that data is data taken from the computer game, which are then compared with the solutions of the differential equations. There is something else that we can show. So let's take this again. And let me show you a glider. So let's change the aircraft. Let's put a glider. There should be a glider here somewhere with big wings. That one, Jantar, that one. So there is the glider. And I think if I go like in a certain way, I can make it loop. And maybe it's going to make you motion sick. It might be the case. I don't know. Oh my goodness, this is so hard. Let me see if I can see it from the outside somehow. So now you can see that the glider is looping. Let's see. Yeah. Oh, it's losing control somehow. Let me show it from the outside. It's very difficult to see here. Follow cam, maybe. Well, it's kind of looping. I don't know if you can see it. It's very difficult. Maybe free cam. Let me try a free cam. Oh, I lost the glider. Darn. I always lose the glider when I use the free cam. But we can see it. We can see. Let me go back to the camera. Sorry about that. And put the cockpit camera. Oh yeah, that's going to be good. So it's looping around, as you can see. So it goes up and up and up, and then it's coming the other way. And then it's looping constantly. So I can take this out before we all get sick. Sorry about that. So if we do things here, let's run this piece of code here. And here, I don't know what the parameters are. This drag and lift and gravity. So you can change here the parameters. So for instance, if we put a lift that is much higher than the drag, we can get something interesting. Let's see. So you can see here, for instance, this plot that you see there is the height as a function of time. So it's kind of oscillating in height, but it's not. And this is the trajectory of the glider on the plane of the motion. So you can get different behaviors as you run the calculations. And of course, you know, if you have data from a 747 or a 737, you can think about fitting the data by fitting just, I don't know, the drag coefficient. In this case, the drag coefficient for the 737 was 6, something like that. So you can see that the behavior of the glider, of the differential equations glider, is in very good agreement with the data points that we extracted from the instruments in the cockpit. So that is a fun activity to do with the students. Then the other thing the students do is to, you know, calculate things. So for instance, this is a project by one of the students that changes the gravity and the density of the planet, the atmospheric density of the planet. So gliding, say, in Venus or gliding in Mars is dramatically different. So, and you can see what she's doing. She gets the code that I gave her. And when she runs it normally, it runs for Earth. But then when she puts the gravity of Mars here, instead of the gravity of Earth, changes the variables and changes the names of the variables to reflect the M from Mars. And then also changes the density into these parameters, the density of Mars relative, the density of the atmosphere of Mars relative to the density of the Earth. And here is the, in Venus, how it is. So this is Mars, and this one here is Venus. In Venus, there is very low gravity, and the density is very high. So if you have a high lift to drag ratio, you can see those loops happening. It's looping and looping and looping and looping and looping around. So this is Y here and X there. So look how it behaves, the glider. It starts to loop around. And then at some point, it's not enough to loop. So it goes in this particular way. And if you remember the 737, it behaved like this, like a little step. That's what we saw when we saw the aircraft, that KLM aircraft. And what we saw in the glider, which is this one. Let's see if it's still looping. Look, it's still looping. You know, it's still going around and around. So we can actually close it because otherwise we're gonna get sick. I'm getting sick myself, so let's stop it. So this went very well. The students love it. They value very well the resources available for them, which are all free, by the way. They like the class essentially. It worked fantastically well. For instance, they appreciate. This is typical of the things that they said. That really like lessons on realistic applications. And yeah, and they work as group in their project. So it was great. It worked out great, I think. So computer games, you can use them to illustrate and explore differential equation topics. The students really enjoy to have something they can relate to. And differential equations is the ideal class to do that. We use basic Wolfram Cloud accounts, which are free and with permission. We also use Creative Commons license books that are also free for the students, and my open math problem set that was inherited from Professor Dom. So thank you so much. Thank you.
Thank you. I mean, I think we appreciated as much as your students appreciated. Showing this live plane is going, KLM is going. I felt like I'm also going there. It's so
oh my
beautiful.
goodness, it was sick, motion sickness. It's very, very dangerous.
Yeah, we were all a little bit worried there. We saw that airplane going down. I'm glad it didn't, you know, it landed safely. That was amazing.
Beautiful. So any questions, please?
I just have a statement. Now, if Brian Winkle were here, he'd say, okay, now your job is to write this up and to submit it in the double-blind, peer-reviewed, semioed, you know, and that would be awesome because it was extremely interesting. And the fact that the students are so interested in it and see the real-life application is fabulous. So that would
it's very nice, but it is a very difficult mission to accomplish, to get the students to program, you know, and to actually pass the fear of computers, you know. But they are used to gaming, so I think that, you know, gaming is almost close to programming, you know. In a way, you have to be a bit of a nerd to be a gamer as well, you know. So there is a community of gamers there that we can address. And the other thing is very important for me, that the things are free. So if they didn't allow me to use the Wolfram Cloud for free, I probably would.
I was going to ask about that. I'm sorry, just because my students are using Wolfram Cloud. I didn't ask for any permission. There's a free account. You just sign up for it. So
apparently, I think that if you use it, corporative use is not allowed. So if you are using institutional use, it's not allowed. I think we can use it as long as we are a few. But if there are quite a few of us, then we will have to pay, I think, which is fair enough.
I see. Yeah, right.
So, you know, I asked for permission because I noticed this institutional thing, but I think we should be fine. The other thing I wanted to say is that in terms of the investigative qualities of the students, you know, some of them are extremely, like, amazingly, I don't know, like creative, you know. For instance, thinking about changing the gravity, but many things that you think that they might do, they will not do, and you have to encourage them. And also group projects, they can actually get angry with each other. And in the gliders project, I think they got angry with each other. I felt a vibe there while they were presenting that it was not okay, but it worked out great. Yes, the most popular project was Models of Love, which includes love triangles and stuff like that. So that was, you know, super funny as well.
So please tell us about your game. How did you get this?
The game, very good question. You are fantastic. That is such an important question, the game. So the game is called GeoFS and it's for free. So if you go here to geofs.com, let me put it in the chat. And it's very simple to use. So if you click on fly, it will already, you know, it will already fly. So let me put it in the chat. So if you want to, you know, copy paste it somewhere, you can have it. And of course it has like, you know, drag and lift on it, you know, so it's kind of flies semi-realistically.
So
And you
people,
click on fly and then you can, well, there are ads, unfortunately, so close the ads, and then you will be flying somewhere. And you can use the cursor keys to make it move.
these are like close to the real data.
Yeah. So the data, this data is extracted from the game.
Mhm.
So it's actually, and close, I don't know. For instance, if you fit the differential equation, which I have it here somewhere.
Mhm.
So one cool thing to do, but it's pretty difficult to do in Mathematica, is
Mhm.
to actually fit use the differential equation to fit data. So determine the parameters of the differential equation by a least squares procedure. The students don't do that. They try to put, you know, the correct lift to drag ratio into the computer. That's the activity. But if you fit, then you can get both parameters from the computer game. And in this case, the drag to lift ratio of that plane was about 6. The lift to drag ratio was about 6. So you can, yes, the game is very nice, and you can use it to get data that is semi-realistic. You know, I think that this is pretty realistic motion of a plane. When they have no engine.
Every time
Very-
I see you talk about this, I'm learning something new. That was really fascinating about the fitting the curve using the Mathematica to fit the curve. That's fascinating.
It's extremely difficult to do, actually. I thought it was gonna be easier because I'm used to programming language that are not symbolic, you know. So you, in a way, you know, would have some easy way to do such a job, like. But in Mathematica, you have to make some tricks to let them, let Mathematica know that the variables are going to be numerical and stuff like that. So yeah, that was difficult to do, but now I have it working. I spent yesterday until 3 a.m. getting it to work. Because
Yeah,
Scott and I, we want to write a paper about this, but we don't know. We don't know yet.
Yeah, and I think that idea of sharing it with Simeo would be really fun.
Yeah.
it's very interesting, and especially solving it with the Mathematica or least square method parameter estimation. And actually, I like this discussion. It feels like let's not stop here, continue, get more ideas.
Very good. Thank you.
Thank you. Thank you so much.